Right. So our next topic is transistor characteristics and application of transistors for various applications like amplifier, switch and an oscillator. Okay. So these two applications we'll see. So basically BJT, bipolar junction transistor. So it will have two types of carriers, bipolar, both electrons and holes will contribute for current, and it has junctions, and a transistor, the name, so basically we use common emitter configuration because it is a 3-terminal device. We have to keep at least one terminal common for its applications in various fields. Like we need at least 2 terminals for input and 2 terminals for output. So at least one terminal must be kept as common. So for all these applications, I keep emitter as a common terminal. And for example, I am considering an NPN transistor. Okay. So for especially for amplification type of applications, for amplification, we need to keep this emitter base junction in forward bias. So let's say this is NPN transistor, we have to give positive potential to base and negative potential to emitter. This emitter base junction must be forward bias and collector base junction must be reverse bias. So this is, since this is NPN, we have to keep a higher positive potential here to collector, and to base we have to give either negative potential or lower positive potential. So then only this junction is considered as reverse biased. Okay. So let's say if you give 5 volts here, you have to give more than that, more than 5.7, let's say, more than 5.7 or at least 6 volts here. Then what happens? This junction will be reverse biased. So this remains, collector remains at higher positive potential and base junction, base terminal is at the lower positive potential. Okay. So we have to give, that is why we show a double battery here, a double celled battery. Okay. So now what happens if I give some potential to this? So I gave 5 volts, let's say here. So this emitter base junction is forward biased and some carriers, so this is more than whatever knee potential for the forward biasing of the diode. So we need to give at least 0.7 volts for this junction to start conducting. Right? In forward bias, we need at least to supply 0.7 volts for starting of current conduction. Right? So since the applied voltage is beyond that, current starts flowing through this. So let's say some 100 carriers enter this region because of the forward bias. And base terminal, base material is very narrow, very slim in size, so it cannot capture all the 100 carriers here. At most 4 to 5 carriers will come out of base and remaining carriers will remain over there. So if I give a reverse potential, reverse bias, so I am applying a higher positive potential to collector. So what happens? All the electrons that enter here will go through collector and will be collected at the other end. So if I raise this potential, so I am taking VCE and output current. This circuit can be constructed more effectively, like I have to give a resistor also here. Let's say I am giving VCC potential here. I call this as VCC, voltage supplied to collector alone. So this is VCC, and let's say this is RC, resistor connected to the collector. Okay, this is an alternative way of representing the transistor circuit in common emitter configuration. Okay, so here input is the base current supplied to the base, and on output we can see two things here. So let's say this is VCE. VCE is from collector to emitter voltage. So the equation can be written as VCC is equal to ICRC plus VCE. So the total voltage applied here will be divided between load resistance, because ultimately we have to connect this transistor to some load resistance. Let's say you are using it as an amplifier. Instead of this load resistance, you will have a speaker. Okay, on the input side you will have some microphone, let's say. So whatever signals received from the microphone will be amplified and transmitted to the speaker. Okay, so we have to show this load resistance compulsorily in the circuit. I mean, this is for basic understanding, but ultimately there will be a load resistance here in the output circuit. Okay, so whatever voltage supplied here will be utilized for two purposes. One, voltage drop across the resistance; another, voltage drop from collector to emitter. So because on the other end you have ground, so this has two components. And another equation that governs the transistor operation is this: IE is equal to IB plus IC. So whatever carriers enter through emitter will be collected either from base or from collector. So whatever enter through emitter will be collected from base or from collector. So IE is equal to IB plus IC. So these two equations will govern the entire activity of the transistor. Okay, so what I am doing here, so I am trying to collect all the whatever 95 electrons. Let's say 4 5 are collected at the base, remaining 95 I need to collect from here. So I am raising the potential. So if VCE increases, current will start increasing from, let's say, 10 electrons, 20 electrons, 50 electrons, 90 electrons. Once all the 95 electrons are collected, the current remains constant. Further, even if you increase VCE, current will not increase. Okay, so this is for a particular value of IB. Let's say some value. Now I am raising the value of IB. I am going to 20 milliamperes. So what shall I do? What should I do to raise the value of IB? I have to increase this value, right? I have to keep it at, let's say I make it 10 volts. So then this reverse bias condition will not be satisfied until I reach 10 plus voltage here. So up to 10 or 11 volts, no current will flow. After 11, once that VC value reaches sufficiently high value, then the current starts flowing through it. Right? So from 10 and 11 I need to go up to, let's say, 15 volts to capture all the electrons. Now let's say for 20 milliamperes I got 200 electrons. 200 minus 5 or 10, 190. Okay, so I need to raise the value of VCE beyond this limit to capture all the electrons of 190. And once the 190 count reaches, current remains constant. Okay, the same way if I raise IB value further, this is the situation. Okay, and before that, so if VCE value is lower than this, what is the situation here? Here both the junctions are forward biased. If VCE value is sufficiently low, both the junctions are forward biased. Right? So here this junction is forward biased. So this voltage is less than this. Let's say this is 10 volts and this is 6 volts. So this junction is also, lower positive and higher positive. So P side you got higher positive and on N side lower positive potential. So this is also forward biased. So what current will flow through it? Current enta flow avutundandi? Now the current flows in this direction. So this is forward bias. The carriers will move in this direction. Electrons will move from N to P. Right? So output current, so I have to go to this equation. So what happens here? So VCC is equal to, VC is negligibly small, VC is very low. So VCC is equal to, in this region, VCC is equal to ICRC. VC is negligible. So no voltage will be dropped here, entire voltage will be dropped at this location only. VCE is 0. So when VCE is 0, so that is the maximum. So IC is equal to maximum current ఏమవుతుందండి, saturation current అనేది IC maximum is equal to VCC by RC. So that is the maximum current when VCE is 0. So this condition where entire current flows only through the resistor and VCE becomes 0 is called off state of transistor. It's called off state. Off state అనేది ఎప్పుడు వస్తుందంటే when IB is very large and VCE is 0. If the input current is very large, our input potential is very high, so that the second junction, collector based junction, is also forward biased. So both junctions are forward biased. So both junctions are forward biased and input current is very high, output voltage is 0. This is called off state. So when input is very high, transistor goes off. Next condition, if I disconnect this, if I make IB 0, so I'm going to the other extreme. So here IB is very high, other case if IB is 0. If IB is 0 what? So both the junctions are reverse biased in this case. Even the input junction is reverse biased. So both reverse biased. No current flows through the circuit. IC becomes 0 and that is called on state. Why is it called on state? So when IB is nearly 0, IC becomes 0. So VCE is equal to VCC, which is maximum. So here IC is equal to VCC by RC, which is maximum. So what do you see? Entire voltage will be dropped here. Let's say you are supplying 10 volts or 15 volts here. Entire voltage will be dropped at VCE. There is no voltage drop across RC. అంటే ఏంటంటే on state, the current whatever is flowing, you can fetch it from the transistor only. Entire voltage drop is now across the transistor. So I call it as on state of transistor. And this is off state of transistor. Okay, so these are the two states where a transistor can be operated. So if IB is very small, output voltage is maximum, will be equal to VCC. And if IB is very high, output voltage is 0, current is maximum, it is called off state of transistor. Okay, and next comes the small signal analysis for transistor. What happens if I give a small signal at the input? So now I am trying to amplify a signal, some voice message or some voice converted to electric signal. I am connecting a microphone. So now this signal has to pass through this and I have to get something at the output. So what happens? So the first thing, to push this signal entirely through the transistor, what is the first condition? I have to keep this emitter base junction forward biased. That is the first condition, right? So I have to push this entire signal into positive quadrant, and also I have to ensure it is above 0.7 volts, right? Let's say this is +1 and this is -1. I have to add 1.7 DC. So if I add 1.7 to this signal, what happens? This is +1, -1 plus 1.7. What do you get? So everything shifted above 0.7. This is now 0.7 and this is 2.7. Right? So once if I push this entire signal into positive quadrant, then this transistor will operate in amplifier condition. Right? So it will be here in between these two. So I have to ensure my transistor operation should be in between these two. So this is the operating region of the transistor. So now what is my condition? Whatever IB value changing from above 0, 10, 20. So where should I give my input signal? This is my input signal. Here IB, at this point IB is near to 0 and it is varying 10, 20. Okay, so this is my input signal. Is that clear? So whatever input signal I am giving, I am representing it here. So it is varying between just above 0 to all positive values. Okay, now for these variations, what is, I mean, IB value is rising, falling, whatever. There is a variation in value of IB. So how does it affect VCE and how does it affect IC? That is right. So if IB rises, what happens? What happens if IB rises? IB rises అనుకోతే ఏమవుతుందంటే IC also increases. If IB increases, I mean here IB is 0, here IB 10, IB 20. So if IB rises, IC also increases. So IC increases and then falls, becomes, this is what I get at IC. And if I use this equation, so since IC is varying like this, I mean I keep RC as 1 for simplification. So if IC increases, VCE should decrease. If IC increases, VCE should decrease. So if IC decreases, VCE should increase overall. So what is the final outcome? So if I take a transistor like this, so if I give some signal here, it will be reflected in the same way across RC, because IC varies in line with IB and VC varies opposite to IB. Right? So, and everything is derived from whatever VCC we are supplying here. So whatever voltage you are supplying through the battery is redistributed between ICRC and VCE in a manner similar to the input signal. Let's say this is 10 volts, that is 10 volts. What do you get here? This total should be 10 volts always. So let's say this is 5 volts, this is 5, total is 10. This is, let's say, 7.5, this is 2.5, total is 10, 5, 5, 2.5, 7.5. This is what you'll get at the output. And what is here? This is 2.7, 0.7. So that activity is called biasing, adding some DC voltage to keep the entire signal in positive quadrant. It's called biasing. Biasing ante ఏంటండి అసలు? డిక్షనరీ మీనింగ్ ఏంటి? డిక్షనరీ మీనింగ్ ఏంటి బయాస్ అంటే? ఐఎమ్ బయాస్డ్. బయాస్డ్ అంటే ఏంటి? ఒకవైపు ఎక్కువ సపోర్ట్ ఇవ్వడము, లేదు ఎక్కువ పార్షియాలిటీ. సో హియర్ బయాసింగ్ అంటే the biasing is towards positive quadrant of the current. సో ఇక్కడ ఈక్వల్గా పాజిటివ్ నెగిటివ్ క్వాడ్రంట్స్లో ఈక్వల్గా డిస్ట్రిబ్యూట్ అయినటువంటి సిగ్నల్ని మొత్తాన్ని మనము we're pushing entirely into positive quadrant. That activity is called biasing. ఇక్కడ ఈక్వల్గా డిస్ట్రిబ్యూట్ అయిన సిగ్నల్ ఏం చేస్తున్నాము? Pushing entire signal into positive quadrant. That's called biasing. Okay. So what is the outcome? You're again getting a varying current. So మీకు డిగ్రీ థర్డ్ ఇయర్లో వచ్చి ఉంటాయి వేరియింగ్ అండ్ ఆల్టర్నేటింగ్ కరెంట్స్. ఆల్టర్నేటింగ్ కరెంట్ అంటే ఏంటి? AC. Alternating current means the signal varies between positive cycle and negative cycle alternatively. So if you get one positive cycle, next to that will be compulsory a negative cycle, then a positive, negative, positive, negative. Alternatively, it varies. So this is called AC. Direct current, either positive or negative, only one side. And if you mix these two, this is not alternating current, this is not direct current, this is called varying current. The current varies but in a single quadrant. Let's say if you subtract them, what do you get? Everything is in negative quadrant. So it is a varying current but not alternating current. Here also you are getting varying current as output. Okay, there is no zero, entire signal is lifted up by a value which may be equal to whatever average of ICRC and VC. Okay, so this is what an amplifier does. So ఇప్పుడు amplification ఎంత జరిగిందంటే, so if I shift it back to original state, let's say if I remove the DC component from this, what I get? DC component ఎంత రిమూవ్ చేయాలంటే, how much should I remove? 5 volts is the DC level in this. So if I remove 5, what I get? 0, 2.5 minus 2.5. So original input signal is what? Plus 1, 0, minus 1. So I gave 1 volt peak signal in the input and I got 2.5 volts signal in the output. So the input signal is amplified by 2.5 times. So amplification factor is so amplification అంటే అసలు ఏంటంటే what is going on actually? What do we assume actually? The input signal is entering into some circuit and it is being stretched up. Stretch అయిపోతుందనే కదా ఇప్పటివరకు ఉన్న assumption, probably. It's not stretching up, it is generated from the DC voltage supplied to the collector in a manner similar to the input signal. So a new signal is generated by seeing as a replica of input signal. So that's called amplification. Okay, so if you give this circuit I mean, if you want to amplify it further, if you want to double it, what to do? So give this to next level, another circuit, another same amplifier circuit, common emitter amplifier. So what happens? There is a DC component already added to it, right? And this is far beyond the bias voltage. So if the current, input current becomes far and far more higher, what happens? Transistor goes off. Then limit ఏంటంటే ఒక certain limit cross చేస్తే the input signal becomes higher and higher, transistor goes off. You cannot amplify it further. So దానికోసం ఏం చేయాలి? You remove the entire DC component here and add whatever biasing potential required at that level additionally. Okay, so for that purpose, to remove the DC component, we use a capacitor here. Capacitor equation ఏంటంటే the opposition offered by capacitor is 1 by 2 pi Fc. When frequency of the signal is 0, opposition offered by capacitor is infinity. So it stops entire DC current and allows only AC current. Okay, so output after this capacitor will be like this, 0, 2.5, minus 2.5. And further, if you need any further amplification, you may need an additional bias. Okay, so that will be taken care by this circuit itself, right? So మామూలుగా biasing ఏం చేస్తారంటే fixed bias, you'll add directly a DC component to the base directly. This is one configuration. Another configuration, you take from the same source, from VCC, add additional resistance. Otherwise, use a voltage divider bias. There are different kinds of biases to maintain the stability. But whatever way, ultimate aim is to shift the entire signal into positive quadrant. Is the entire purpose of biasing. Okay, so that's about RC coupled amplifier. Okay, so now what is the situation here? Whatever input signal I am giving here will be flipped in the output. VCE is quite opposite to the input signal, 180 degrees out of phase, right? Is that clear? So VCE is opposite to input signal. There is a phase shift of 180 degrees, right? So that part I'll continue. So one more thing. So here the input junction is forward biased and output junction is reverse biased. So input junction resistance is very low. This is forward biased, and output junction resistance is very high. So current is flowing from a low resistance region to a high resistance region inside the transistor. So that is why the name transfer resistor. Transistor. So charge carriers are transferred from a low resistance region to high resistance region inside the device. That's why it's called transistor. So bipolar junction transistor. It has two types of carriers, two junctions, and it transfers carriers from low resistance to high resistance. I mean, for normal operations. For other operations, okay, we'll see. So next upgradation to this concept is feedback amplifiers. So what happens if I feed back a portion of the output amplified signal to the input? So let's say I'm taking a amplifier circuit with amplification factor A. A is the amplification factor, and let's say this is V in and this is V out. So A is equal to V out by V in. So I'm taking a fraction of the output signal and giving it back to input. This beta is less than 1. So if the output is 10 volts, I'm taking, let's say, 0.1, 10% of the output and giving it back to input. Okay, so I may add it or I may subtract it. There are two possibilities, either positive feedback or negative feedback. Okay, we'll see both the cases, and let's say for the time being I go for positive feedback. Okay, so I am shifting how to name them. Actually, this is my input signal and this is my output signal, so I have to name them properly. This is my input signal, this is my output signal, and the basic amplifier input, basic amplifier output, let's say I mark them as B, base amplifier. Okay, so my V in and total amplification factor with feedback is V out by V in. The base amplifier amplification is V out base by V in base. Amplification with feedback V out by V in. I am giving a positive feedback, so V in B is equal to V in plus beta times V out B. So I am giving a fraction of the output of base amplifier to the input. This is my V in plus beta times V out B is my V in B. Okay. So now if I divide it with what I get, so 1 is equal to V in by V in B plus beta times V out B by V in B. So 1 is equal to V out is what? cannot write like this. Let's say I work out with this. AF is equal to V out by V in. V out is what? V out B minus beta times V out B. Taking the output in parallel. So instead of all this nonsense, equations will be a little more easier now. So A is equal to V out by V in B. AF is V out by V in. V in B is V in plus beta times V out B. So from these three equations I have to compare AF and A. Okay, and what is that I need to eliminate here? The unwanted factors are these. These are the unwanted factors. V in B is the unwanted factor here. I need to eliminate that. Right? All I need to know is V in and V out, whatever beta factor. So unwanted factor is V in B. I need to eliminate that. Somewhere if I substitute the value of V in B, I'll get everything out. So A is equal to V out by V in plus beta times V out. Is that clear? So now what is the AF? VF by V in. So if I divide it with V in on both sides, so V out by V in by V in by V in plus beta times V out by V in is what? AF by 1 plus beta times AF. So I got three equations and I need to eliminate V and B, which is of no use for me now. That information should be eliminated. So I eliminated V and B here. So what I get? V out by V in plus beta times V out. And I try to convert in terms of the known factors AF. So V out by V in by V in by V in, beta times V out by V in. So what did I get? A is equal to AF by 1 plus beta times AF. So if I rearrange it, I need to get the value of AF. How to get that? AF A into 1 plus beta times AF is equal to AF A plus A beta times AF is equal to AF. So if I take AF in common, so this is the equation I get for positive feedback. So if the feedback is positive, if beta is positive, I get this equation. If beta is negative, that equation turns its sign. AF is equal to A by 1 plus A beta. that's a different story. So now the required factor is this: if A beta becomes equal to 1, somehow if I manage, so beta is less than 1, A amplification is greater than 1, somehow if I manage, I mean beta is under my control now, I can tune it to whatever level I want, and somehow if I manage this beta to be equal to, I mean product of A and beta equal to 1, then what happens? EF is equal to A by 0, which is infinity. I get infinite amplification. That means what? Even without input signal, I can get an output signal. So only when, if I maintain positive feedback. So here the first condition I am taking is tapping the output in parallel. So voltage remains same, output voltage remains same for both the cases, with feedback and without feedback. Okay, current may vary. And adding it in series here in the input. So here in the input section voltages will add up, and output section voltages will remain same. Okay. So under those conditions, if I maintain A beta product is equal to 1, then I'll get an output signal without an input signal, and that condition is called oscillator. The only thing we need to do is positive feedback with controlled feedback factor beta. Okay. So there are different possibilities. One simplest way is RC coupled RC phase shift oscillator. So I am taking a normal transistor amplifier. So with all stabilization factors like voltage divider bias with emitter bypass capacitor, this is my amplifier. Okay, so to this amplifier, basic common emitter amplifier with voltage divider bias. Okay, now I am taking output from here, so this is 180 degrees out of phase from the input. Now I add 3 RC components, so resistance and a capacitor, again a resistance and a capacitor, and I give back to input. So that the combination of all these 3. So usually capacitor produces a 90 degrees phase shift. So if you use just 2 capacitors, we'll get another 180 degrees phase shift. But we cannot, we have to introduce another resistance also, because we have to tap only a fraction of the output and give it back to input. So I'm ensuring each combination RC produces 60 degrees phase shift. So each combination produces 60, 360 is 180. So input becomes positive. Now I don't need to give any input signal here. So I can remove my input signal and give 3 RC phase shifting circuit, RC phase shifting components in series to the output. so that a fraction of output will be feedback to input in a positive manner. So this is called RC phase shift oscillator. So we don't need to give any input. Whatever charging and discharging cycles of this capacitor will produce the initial wave. So that is why on the output you may see one charging cycle of the capacitor, further followed by discharging, and once one cycle completes you will get entire oscillations. So this is the output of the circuit, right? A similar way you'll have other oscillator circuits also, Colpit oscillator, Wien bridge oscillator. Wien bridge is a part of bridging networks, like it was initially developed to measure the unknown resistance using parallel and series combinations of resistors and capacitors. This is the Wien bridge. So this was used to compare or measure an unknown resistance by using the combination of these RC parallel and RC series combinations, so that the effect of capacitance gets cancelled. I mean, if at all any inductive or capacitive effects occur in the circuit, they will be cancelled out in this component and you get a pure resistance value. And this combination is now used to produce whatever 180 degrees phase shift, and instead of these three RC components, if you give one input here and take the output back to feedback, it's called Wien bridge oscillator. And Colpit's oscillator also similar way, you can produce 180 degrees phase shift using some components of R and C. Colpit's oscillator contains combination of L and C components that produce a 180 degrees phase shift. So there are three different types of oscillator circuits. RC phase shift. So this is LCR tank circuit. I mean, that can be used to generate oscillations of a particular frequency, 1 by 2 pi root LC. And here for RC circuit, what you get, the frequency is given by 1 by 2 pi root 3n times RC. So here n is the number of pairs of R and C. So for this 3-pair circuit, it is 1 by 2 pi root 6 RC. RC is not in the square root. Here 1 by 2 pi root LC, both L and C are in square roots. And for Wien bridge oscillator, the frequency is given by what? Check the equation. So somewhat it is 1 by RC. Okay, so here n is number of RC pairs.
1 by 2 by RC.
1 by 2 pi RC. So that's all about oscillators. So further we will see how to use transistor as a switch, that is in the next session, where it can be used to generate square waves. I mean switching between on state and off state continuously. That we will see in the next session.